Okay, Quantum1 tutorial question number 6. Okay, part A. A source of ultraviolet light has wavelength 2.55 times 10 to the power minus 7 meters. Calculate the energy of a photon of this wavelength. Well, the energy of a photon is given by this formula, E equals to hc over lambda. H is the Planck constant, c is the speed of light, lambda is the wavelength, so you just sub in the values and you get the answer. 7.80 times 10 to the power minus 19 joules. Part B, we have a diagram showing the photoelectric effect experiment. Okay, the source referred to in A, which is here, the ultraviolet light source, illuminates a zinc plate, which is here. The zinc plate is cleaned, and that's what we want if we want to demonstrate the photoelectric effect. This zinc plate is placed just a few millimeters beneath a piece of gauze, as shown in figure 6a. So this gauze got many openings, so it let in the ultraviolet light, and the main action is when the ultraviolet light strikes the surface of the zinc plate. And what happens when the UV light hits the zinc plate? Well, photoelectric effect. Photoelectrons, which are just electrons, the electrons are emitted from the plate. Then when the electrons are emitted, they will be all attracted to the positive gauze. Okay, it's positive because it's connected to the positive terminal of the battery. This whole setup is actually a variable voltage source where they can vary the voltage here by sliding the slider. When you slide to here, you got more voltage. When you slide to here, you got lesser voltage. So this acts like a variable voltage source. So in experiment, they vary this voltage, and when they vary the voltage, they measure the current. This current will sort of reflect how many electrons are collected by the gauze. The more current, it means got more electrons are collected by the gauze. If there are no electrons collected by the gauze, then you have zero current. So they actually did an experiment using different V and measure the current for different V. Okay, question B, part 1. Explain why for curve A, the photoelectric current, which is this value, reaches a maximum value no matter how large the V is made. So you can see from here, even though they have increased the voltage, the current is still the same. Well, what happens is that this current is a reflection of how much electrons has been collected by the gauze. But the number of electrons that's emitted by the plate actually only depends on how much light you shine onto the plate. The more light you shine onto the plate, the more electrons are emitted and collected. The less light you shine on the plate, then the less electrons are emitted and collected. So if you look at curve A, throughout the whole experiment, they use a certain fixed amount of intensity. So if they use the same intensity throughout the experiment, so if they shine the same amount of light, they'll get the same number of electrons emitted per second. So that's the first point. For a given intensity of illumination, you have a certain fixed number of electrons are emitted per unit time, and that's regardless of what voltage you use. Use high voltage, less voltage, doesn't matter. Because you use the same amount of light, you get the same number of electrons emitted per second. Then when all the electrons has been collected by the gauze, that's where your emitter will register the maximum current. So that's why even though you have high voltage, it doesn't affect the number of electrons emitted because it's the same. And when all the electrons emitted are collected, you get the maximum current. Over here, you got lesser current is because at first when the voltage is not high enough, there is still the same number of electrons emitted per second, but there are some stray electrons that heading in different directions, so they are not collected by the gauze. So that's why when you increase the voltage, the positive voltage will now be able to attract all the stray electrons back to the gauze. So at this point, when the voltage is high enough, when they have collected all the electrons emitted, then they get the maximum current. Okay, so that's B part 1. B part 2. Now what they do is they reverse the battery so that the voltage V is now negative. So the reverse here is negative. So this Gauss will be negative. When it's negative, electrons are negative charge. So when the electrons are emitted by zinc plate, they will now be repelled by the negative Gauss. If they are repelled by negative Gauss, so why there are still some electrons still able to reach the Gauss? Because when we see that when the voltage is negative, there's still some current detected. That means there's still some electrons collected by the Gauss. So why is it that the electrons that are repelled by the Gauss and yet we can still detect, we can still collect the electrons? Well, what happened is that the electrons are actually emitted from the zinc plate with all kinds of speeds. Some slow, some very slow, some are very fast. So although all the electrons are repelled, the slow is a slow one, okay, that will get stopped halfway. But the fast one will be able to have fast enough to reach the Gauss. So your first point is to tell them that the electrons are emitted all with different speed, different Ke, ranging from 0 speed all the way to maximum, certain maximum value. Then when your Gauss is made negative, yes, they'll try to repel the electrons, but only the less energetic electrons. Okay, there's a spelling error, should be less energetic without the S. Okay, so the slow one will get stopped halfway before it reach the Gauss. But the others one that are energetic enough, they are more energetic electrons, those are the ones that won't be stopped halfway. They'll slow down, but they still manage to sort of overcome the applied PD and arrive at the Gauss. So that's why there's still some electrons manage to reach the Gauss, because those are the faster ones. See part 1. Now they increase the intensity of the light source and repeat the whole experiment again, and to get curve B. So you get a curve B. This is the one that they repeat at higher intensity of the light source. As you can see, at curve B, they register more current than curve A. So the question is, why does the curve B register more current than curve A? Well, first of all, the current is a reflection of how many electrons are collected and how many electrons are, and that depends on how many electrons are emitted. What happens in curve B is that you are actually using higher intensity light source. So what is the difference between a high intensity light source and a low intensity light source? Well, the difference is that in the high intensity, it means you have more photons. A light that's bright is bright because there are more photons. The light is dim is because it's less photons. So when you increase the intensity of the light source, you are actually increasing more photons striking the metal surface per unit time. Okay, this is the formula. I intensity equals to N over T times HF over area. N over T is the number of photons per second. If the others are the same, H same, F is the same, area is the same, so intensity is proportional to the number of photons emitted per second. So if you have a higher intensity, it's because there are more photons emitted per second. So now there are more photons striking the metal surface per second. What happens when more photons strike the metal surface? Then correspondingly, proportionally, you will get more electrons that's ejected from the metal surface per unit time. And when you have more electrons ejected and you have more electrons collected, then the emitter will register more electric current. Okay, that's C part 1. Okay, C part 2 suggests why the value of V necessary to prevent any photoelectric current remains constant. Well, if you look at this one whole string of words, value of V necessary to prevent any photoelectric current is referred to this V value. There are other V, but other V there's still some current. Only this particular V where the current becomes 0. This V has a name, it's called the stopping potential. The value of the voltage that make the current 0. Okay, stopping potential. So the question is actually asking you, why is the stopping potential remains the same? As you can see, these two graphs, they repeat with different intensity, they have different currents, but they all have the same stopping potential. The current all drop to zero at the same value of the voltage. So why is the stopping potential the same? Well, what we need to do is we try to figure out what does stopping potential actually depends on. What are the factors that affect the stopping potential? Well, to find out what are the factors that affect the stopping potential, we have to invoke the Einstein photoelectric effect equation, which actually tells us exactly what's happening in the photoelectric effect. This is the Einstein photoelectric effect equation, which says that what happens is that you have one photon, HF energy, absorbed by the electron, and it uses part of the energy, which is phi, work function, to escape from the metal surface. Then the remainder will appear as the maximum K of the electrons, and that will be related to its stopping potential, the stopping potential. So if we rearrange EVS equals to HF minus 5, that means the stopping potential actually depends on only two factors, HF and phi. Okay, so first thing you tell them, stopping potential Vs does not depend on intensity. It doesn't appear in this equation. It's not affected at all by intensity. You're only affected by the photon energy HF and the work function phi. And work function phi actually is dependent only on the type of metal you use, whether you use a zinc plate or you use other metal. So in this case, since you are using the same frequency of the radiation, so HF is the same, energy of photon is the same, you're also using the same metal, the zinc, throughout. So the work function also same. So if this is same, this is same, Vs will also remain the same. Okay, so that is C part 2, and that is question 6.